let's now see how can we check the properties of different estimators. Let our sample be of the size 9, so we have 9 observations from x1 to x9, and their distribution is this one, so they can take values 0 and 1 with probabilities 1/2. So binomial distribution with parameters 1 and 1/2. And E of xi is equal to mu, and we want to estimate this mu. Actually, no, that's wrong. So in this case, we know mu, so we can find that mu is equal to real value of mu is just 0.0 times 1/2 plus 1 times 1/2, that is 1/2. So real value of mu is known here, but because this is an academical example, so in real life, when we estimate something, this distribution is at least partially unknown. So, and 7 estimators of mu are being considered. So they are mu hat 1 is 0.45. So it is non-random, it's a constant, like in my example. So they say that the estimator can, it is possible for the estimator not to depend on the sample. So this estimator, mu hat 1, is always equal to 0.45. Then mu hat 2 is x1. Mu hat 3 is the sample mean, so it's 1/9 times the sum of x's. Mu hat 4 is so is x1 plus 1/3 x2, and mu hat 5 is 2/3 x1 plus 2/3 x2 minus 1/3 x3. And so the question is, are these are these estimators unbiased? Are they consistent? No, as the sample size is finite, let's just no questions about consistency. Are they unbiased? And which one is the most efficient? So to find if they are unbiased or not, we are to find the expected value of each of these estimators and to check if it is equal to the mu, to the real value of mu, that is 1/2 or not. So let's do this. So actually the bias of an estimator is the difference between its expected value and the parameter that is estimated. So E of mu hat 1 is just 0.45 as mu1 is non-random. So and so it is not equal to mu, that is 1/2, So this estimator is biased. That means that mu hat 1 is biased. And its bias of this estimator is the expected value, so 0.45 minus mu minus 0.5, and this is minus 0.05. This is the bias. Then the second one. The second one, oh no, mu2, mu hat 2. So this is expected value of x1 as mu hat 2 is equal to x1. Expected value of x1 is 1/2, as so the expected value of all x's is, are the same. So it is 1/2. This is equal to mu. That means that mu hat 2 is unbiased. Is unbiased, and the bias is 0. So bias of mu hat 2 is 0.5 minus 0.5 is 0. Then E of mu hat 3 is E of 1/9 times sum of xi's, that is 1/9 times sum of the expected values of xi's, and they are all 1/2, and so this is equal to 1/2, and this is equal to mu. So mu hat 3 is also unbiased. Then, as for the mu hat 4, expected value of mu hat 4 is the expected value of x1 plus 1/3 x2, that is E of x1 plus 1/3 times E of x2. So they are both 1/2. So 1/2 plus 1/3 times 1/2, that is 1/6. So this is 4/6, or 2/3, that is not equal to mu. So that means that mu hat 4 is biased. And the last one is the mu hat 5. So expected value of mu hat 5 is expected value of 2/3 x1 plus 2/3 x2 minus 1/3 x3, that is 2/3 of E of x1 plus 2/3 of E of x2 minus 1/3 of E of x3. So this is 2/3 times 1/2 plus 2/3 times 1/2, no, not plus, but minus 1/3 times 1/2. So this is 1/3 plus 1/3 minus 1/6. And so, yes, this is 1/2. That is equal to mu, to the real value of mu. So that means that mu hat 5 is unbiased. So then, how to find which one is the most efficient? I told you that if we consider only unbiased estimators, then the measure of efficiency is the variance of an estimator. And we see here that some of our estimators are biased and some of them are unbiased. And so in this case, the mean square error, or MSE, is used. The MSE, the mean square error of an estimator is defined as the expected value of the theta hat minus theta squared. Or if we can make some operations based on the properties of the expected value and the variance, and we will get that this is actually equal to the E squared of theta hat minus theta plus the variance of theta hat. This is actually the bias. So bias, squared bias of theta hat plus the variance. So for unbiased estimators, MSE is equal just to variance, as bias is 0. For the biased ones, it is squared bias plus the variance. Let's now apply this for our estimators. So MSE of mu1 hat is, so squared bias, as we remember, the bias is 0.05 squared, plus the variance. The variance is actually 0, so this estimator is non-random, so the variance of mu1 hat is 0. So this is just 0.05 squared, that is 0.00025. So this is the MSE of mu1 hat. Then MSE of mu2 hat. As mu2 hat is an unbiased estimator, then the MSE in this case is equal just to variance. And the variance is, so x1 is distributed so according to this distribution law, and so the variance is just 1 times 1/2 times 1/2. So this is a binomial distribution with parameters 1 and 1/2. So the variance is 1 times 1/2 times 1/2, that is 1/4, that is 0.25. Okay, then mu3 hat, MSE of mu3 hat is, mu3 is also unbiased, so this is also equal to the variance of mu3 hat. And so the variance is variance of 1/9 times sum of x's. So 1/9, this coefficient is squared, so this is 1/9 squared times sum of variances of x's, as x's are independent. So for independent random variables, a variance of sum is equal to the sum of variances. So variance of xi, as we already know, 0.25 is 1/4. So I have here, and this variance is added to itself 9 times. So I have here 1/9 squared times 9 times 1/4. That is 1/36. This is MSE of the third estimator. Now the MSE of mu hat 4. MSE of mu hat 4 is the bias, as it is a biased estimator. Squared bias plus the variance. So we know that the bias is difference between expected value of the estimator and the parameter, and we know that the expected value, we have already found it, it is 2/3, and the mu is 1/2, so the bias is 2/3 minus 1/2, 1/6. So bias, squared bias is 1/6 squared. And then plus variance. Variance of mu 4 is variance of x1 plus 1/3 x2. So this is 1/6 squared plus variance of x1, variance of x1 plus 1/3 squared, variance of x2. Both variances of x1 and x2 are 1/4, so this is 1/36 plus 1/4 plus 1/9 times 1/4. So this is 2/36, this is 1/, so this is 1/18 plus 1/4. So this is equal to 11/36, or in decimal numbers approximately 0.306. So, and the last one is mu 5. MSE of mu hat 5 is mu hat 5 is unbiased, so it is just variance. Variance of mu hat 5. And so the variance is 2/3 squared times the variance of x1, that is 1/4, plus 2/3 squared times variance of x2, that is also 1/4, plus, not minus but plus, as minus 1/3 is squared, So plus, let me say, so minus 1/3 squared times 1/4. So what do we have here? Here we have 9 times 4, that is 36 in denominator, and in the numerator we have 4 plus 4 plus 1, 5. 5/36. So let us have a look. What did we get? MSE of mu1 hat is 0.05. MSE of mu2 hat is 0.0025. MSE of mu3 hat is 1/36. MSE of mu4 is 11/36. So in decimal numbers, this is approximately 0.028. So this is approximately 0.306, and the MSE of the mu5 hat is 4/36 is 1/9. Sorry, 9/36, that is 1/4, that is 0.25. So the most efficient is the one that has the least MSE. And here we see that the most efficient in these terms is mu2 hat. So its MSE is the least one.